Imagine you're playing a guessing game with your friend. He picks a number between 1 to 1,000, and after your each guess, he tells you whether his number is greater or smaller than your guess. What is the minimum number of guesses you need to make? Maybe it's 200 or 100 or 50? No, it's only 10. You will learn why by the end of this video. Binary search is one of the most used tricks in programming. It's the most efficient, consistent search algorithm ever discovered. Formally given a monotonic function f and a Boolean function g that changes from true to false or vice versa at a specific point x, locates that point by continuously halving the interval known for containing x. So for example, let's solve for the function f of x equals x, and g of x is only true when x is greater than 20. We want to find the smallest x such that g of f of x is true. Let our interval be from 0 to 100. If g returns false, the number we guessed and all numbers to the left are eliminated. But if g returns true, all numbers to the right are eliminated. We have to eliminate as much numbers as possible in one guess. For this, we need to maximize the expected value of eliminations. For example, if we guess 70, there's a 30% chance it will return true, which would eliminate 70 numbers. And there's a 70% chance it will return false, which would eliminate 30 numbers. We can calculate the expected number of eliminations with 70 multiplied by 30% and 30 multiplied by 70%. See if you can figure out the general formula. You probably noticed the formula. It's 100 minus x times x over 100 plus x times 100 minus x over 100. We can find the maximum of this function, but in general, if a function is in the form x times and minus x, you will get the maximal value by putting half of n to x. For example, 50 times 50 is 2,500. 49 times 51 is 249. 2,499, and it will decrease more the further you get away from 50. Let's do an example. The numbers are 0 through 13. The middle is the floor of left plus right divided by 2, and our secret number is 10. Since 6 is smaller than 10, this eliminates all numbers smaller or equal to 6. We can set the new left to 7 now. Now 7 plus 13 equals 20, and 20 divided by 2 is 10. Since 10 is equal, we terminate. Now let's solve a harder problem. You're given an array of n integers where n is odd. You're allowed to choose any element from the array and increase it by 1. But you can only do this operation k times. What is the maximum median achievable after k moves? I'll give you a hint. Try to think, can I achieve x after k moves? Instead of what is x after k moves? There are 3 key observations in this problem. The first one is that if you want the median to be x, every value to the right must be greater or equal to x. This means the number of operations we need to do to achieve a median of x is x minus a of I for all I, starting from the median. And the last one is that if you can achieve x, you can definitely achieve any value between the initial median and x, because you've played these games before. What do I mean by that? Let me show you with an example. Let's take this array. The median is 11. Let this median counter keep track of all the medians we've achieved so far. I only need to increase the median until it reaches 15. So let's do that. Since I can only increase elements by 1, I've passed through every element between 11 and 15. What if we wanted to increase it to 16? We'd need to increase the 15 too, because then our median wouldn't change. So my point is, since we can only increase values by 1, we will have passed through every value between our initial median and x. This means we have a Boolean function g that changes from true to false at a specific point. Thus, binary search is applicable. Our left, the minimum value is equal to the median, and right, the maximum value is equal to median plus k. Let's do an example where k equals to 7. Our needed tells us the number of additions we need to make. Initially, our mid is 7, so our needed is 7 minus 4 equal to 3. Let's see if 7 returns false or true. We continue to add 7 minus 5 until we've reached the end. Our needed is 9, which is larger than our k, which was 7. So a median of 7 is not possible with 7 steps. We set our right to 6 and continue. 5 minus 4 adds 1 step, but notice the next element. 5 is greater or equal to our median. We can terminate since it's not going to need any steps anyway. We will set our left to 6 and answer to 5. Now we continue to traverse and add 6 minus 4 and then 6 minus 5 3 times. Our needed is 5, which is less than our k, so we set answer to 6. Since L is equal to R, the function terminates with answer 6. Let's go back to our original problem. Why is the answer 10 for searching 1,000 elements? It's simple. We have the size every time, meaning we eliminate half of the elements from the candidate list, thus needing log of n plus 1 steps. Here's 1,000 step-by-step number of elements that are eliminated. I will try to make an educational video about the topic you want in the comments. By the way, this is an AI voice. Thanks for watching.